Good evening, and thanks for joining our Tuesday night webinar hosted by Texas Instruments. Tonight we're going to get into some of the ins, outs, and math of kicking a field goal. My name is Mike Hewson, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make those tough-to-teach, tough-to-learn concepts accessible to all my students. Today I'm really excited to be joined by our two panelists, Todd Graba and Brad Poznansky. Todd is the STEM division leader at Crystal Lake South High School in Crystal Lake, Illinois. His teaching background is in physics, chemistry, and is currently teaching AP Computer Science principles, and also has extensive curriculum experiences in all high school math and science practices. Todd's main professional development areas for TI are in using the Nspire and Navigator systems in science classes, and with incorporating coding into the classroom or STEM activities with the TI Innovator Hub. So Todd, it's great to have you with us tonight.
Thanks, Mike. Great to be here too.
And Brad's in his 27th year of teaching at Comswog High School. He's been using the TI technology in his classroom ever since he student taught. He's a firm believer that you never stop learning, and that is evident in his pursuit of new and innovative challenges made possible through TI technology. Brad is presented at local, state, national, and international conferences. He coaches 3 varsity sports and really loves to sail in the Caribbean. So Brad, it's great to have you with us as well.
I'm happy to be here.
At this point, Todd, will you discuss our agenda for us?
Yeah, so tonight, obviously we're going to introduce ourselves. We've gone through that. The main bulk of what we're going to talk about tonight then are going to be the math and science behind field goal kicking, and what are the different factors needed to make a field goal from a variety of different distances. We hope to be able to show you then some pre-made activities that are out there on the 84 platform, along with a simulation that we've created here to use with the Nspire and some coding and some Python. And stick around for the whole presentation because A, it's going to be fantastic, but then also because there will be a drawing at the end for some lucky person to win the TI calculator of their choice.
Awesome. Thanks so much, Todd. And Brad is going to discuss our expected outcomes.
Okay, so the expected outcomes for tonight, hopefully by the end of this webinar, you'll be able to understand some of the parameters that are needed to determine if a projectile has the range needed for a successful launch. And in our case, if the football crosses over the goalposts. And we'll hopefully show you how you can access some pre-made resources on the TI websites that you can use in your classroom tomorrow. Also, you can modify or create programs to simulate launching a projectile. That's one of our main goals tonight. So got a lot of different outcomes. Hopefully we have a lot of participation in the Q&A today, and away we go.
Awesome. Thanks so much, Brad. And on that note of the Q&A, we are going to be using the Q&A tonight. If you have any questions for Todd or Brad, use that Q&A window. Send those questions in. We'll also be using the chat window tonight to send those messages back and forth as Todd and Brad ask you questions and engage with you. Use that chat window to respond. We're expecting a large crowd, so your audio is automatically muted. Again, feel free to send them any questions at any time. We'll try and get those questions answered live if we can. As a reminder, this session is being recorded, and we'll provide a link to the certificate of attendance at the conclusion of the webinar. So without any more delay, Todd, you have control. Feel free to share your screen.
Sounds great. Thank you. All right. So let's go ahead and share the screen here and get ready to go. Thanks everybody for being with us here tonight. Let me get the presentation pulled up here, and we'll get rolling. All right, so as we've discussed, the main idea here is kicking a field goal for the win, or just kicking a field goal to get 3 points and get the game closer. Whatever it is, we're trying to figure out how it is to kick a field goal with the right velocity and the right angle to be able to go ahead and get those 3 points. So Brad and I have already been introduced, but here's our information as well. We'll have this slide at the end also for you, so that way if you would like to follow up with us later, you can do that. If you'd like to follow us on Twitter, you can do that as well. I think there's a lot of really good information shared in the STEM education world that is posted up on Twitter, and some of that information is posted by Brad and I and some others in the TI world. So hopefully we can all connect that way as well. One of the things that we have been talking about in the science world for quite a while is with the NGSS standards, making sure that we're following a method and a model for our education that is helping students engage with us, engage with the curriculum, and making sure that students are active learners in our classroom. So following this 5E model is what we're going to be doing tonight as well. The engaging piece is obviously getting the students excited and interested in whatever the content is that we're going to be talking about, and then giving the chance to explore some information about that topic once they have been hooked into it. Explaining then that information is for students to be able to, after they have experienced a phenomenon, seen a demonstration, done a lab, some combination of those, being able to come up with some explanations of what they've seen and why they think that's happening. The elaborate piece really is designed as more of the teacher instruction piece and really trying to drive home those points and help the students really make sense of what it was that they were attempting to explain from what they explored. And then again, the evaluate piece is more on us as the educators and evaluating their learning. But I also think it's important for the students to be able to work with one another through the explain process to gain a deeper understanding, elaborate on that content themselves, and be able to evaluate their own learning before they move forward. And I think the simulation that Brad did an outstanding job coding that we'll show you later here at the end can really help students evaluate if the information that they've gotten from a lab, that will show you that as well, is really data that makes sense or not. And in that process, I might embarrass myself a little bit in a video, but we'll see if we get there. So I'm wearing my Bears shirt today, even though this weekend was not all that great for a Bears fan. But one of the worst memories and recent memories for the Bears was this experience here. It's impossible. Unfortunately, that was more than possible, as the goalpost was hit twice on the infamous double doink at the end of the Philadelphia Bears playoff game, where the Bears had driven down the field and were going for the win and to move on, and it really all just fell apart after that. And so, is it really impossible? Obviously not, because he did it. And actually, this kicker, Cody Parkey, is known as the most accurate kicker in field goal history from the viewpoint of he has hit the goal posts more than any other kicker in NFL history. And that was one of the moments there. So what we need to try to figure out is, what does it take to make that field goal? What does it take to get it through the uprights? And we're going to more explore the distance aspect as opposed to the accuracy left and right aspect. We're not going to get into how conservative forces may impact this and wind resistance and those things. We're taking this from a middle school, high school introductory approach, but getting the understanding of what is happening in the actual field goal itself. So let me get this back up in the slideshow again and move forward into the next slide. Hang on one second. This will be the way to do that. All right. So I would love to hear from you. We would love to hear from you over in the chat window. What makes the difference of whether or not someone is going to make a field goal? What are some things based off that phenomenon that we would like to explore as we're going through that 5E model? So go ahead and put some thoughts into the side window over there.
Leg strength.
Angle, leg strength.
There it is. Velocity, wind.
The holder. Yeah, there it is.
All right.
Yeah, all of these are outstanding ideas that are coming in there. So go ahead and keep putting more in there. Some of those we're going to definitely get into and discuss tonight, and some of them are beyond the scope of what we're getting into here. As you start talking about how the ball may curve as it's in the air. If you start talking about really highly launched projectiles, you could get into the Coriolis effect and those things way beyond the scope of what we're talking about here. But yeah, all these ideas that are coming are great ones. Questions to ask of what path does a football make when kicked? What kind of a function will model this behavior? What are the factors that impact that matter, excluding wind conditions, such as the length, the velocity of the kick, the angle of the kick, those kind of things. Questions of how much does the velocity need to change for a 30-yard field goal versus a 50-yard field goal? And what are the differences between those two? And what's more important? Is it the speed? Is it the angle? Is it the combination of those two? Which of those two plays a bigger factor? Is it how strong your leg is, or is it a factor of which angle you kick at? Which angle is the best angle to kick at? So all of these different things are ways to explore and try to figure out, and that's what we're going to try to go through today as we move forward through this activity. So thanks for the participation. They're all outstanding ideas. I'm going to stop sharing and give Brad control here as he's able to show you the pre-created activity that is already there. So Brad,
Okay.
there you go.
Got to toss me that ball there, buddy.
Yep, there it is.
All right, there we go. All right, so what I'm going to take you guys through here is, I got to find my 84. There it is. All right, so back in 2016, a couple of the guys at Texas Instruments did a webinar and an activity that's on their website. And on one of the slides in our presentation, we have links to both the presentation that they did. It was an hour-long webinar. Also, the direct link to the website where there's pre-printed materials. They'll take you through the entire process. So on the 84, this was called, I think, field goal for the win, or something along those lines, or math for the win, I believe it was. And so on the 84, you preload this program called the Kick. All right, and it takes you into this activity. All right, so the stem behind sports. All right, kick is away, it's good. All right, so it gives us a little scenario. 4 seconds to go. Your team's behind by 1. You have time for a 50-yard kick to win the game. All right, so we're going to try to use some math for the win of this. So they give you a couple categories here. All right, you can do a 50-yard kick. A 50-yard kick where it shows you the height and the velocity of the kick as it's going. You can actually do a custom distance and kick. And then this fourth one has custom distance to kick, and it introduces some defense to the problem as well. All right, so we'll just go over the first one here. So if we choose number 1, all right, after the kick, use trace to feature. So here we get to watch the kick. It's up. And it looks like it's got some height.
Drum roll, please.
Getting closer. The fans are holding their breath. And we need to determine if this is good or not. All right, so we use the trace feature. This is kind of a fun piece with the students. So right here, you can see the X is the distance, and the distance is in feet. And so keep in mind that a 50-yard field goal is going to be 150 feet. The Y is going to give you the height of the ball. All right, so as its progress is being tracked, and the T is the time. So after 1 second, the ball is at 33 feet in the air, and it's 52 feet from the position that it was kicked from. And so here we have a maximum height of 37 feet, and it's 78, almost 80 feet from where it's launched. So as we keep going along the lines, we got to figure out if it's the goalpost height is at 10 feet. So it has to cross a 10-foot barrier. So here we're at basically 49 yards, all right? And it's at 12 feet in the air. And if we press trace one more time at 2.9 seconds, it's at 152 feet. So it's traveled 50 yards, but the height is only 7.8 feet. So here, we don't know if we made it. So this could beg the question of maybe we need more sampling, right? Not every 10th of a second, but maybe every 500th of a second. So we could go into some of those factors, all right? We could solve this as well to figure out the heights as it goes. All right, so this was the TI-84 activity. You can do custom distances, which we'll be doing later in the program that we created. And so this is, again, there's all preloaded activities for the 84 worksheets that are you can modify them using Word files for your students. And there's even an activity there where If you have, I think, a Vernier 25G accelerometer, you can measure how fast your student's leg might be going to get the velocity. So that was the 84 example, all right, that we have. So I'm going to stop sharing that. I'm going to bounce it back to Todd for the next one. Should be coming. Yep, here you are, Todd.
All right, let me pull
Pull up the slides.
Yep. Go back in here.
And when Todd has a slide up, you can see we just took a screenshot of the web page, and we included the links at the bottom for the hour-long webinar by Curtis Brown and Eric Archer, who did the webinar.
Yeah, and so all of these will be made available to you so that you can go ahead and get access to all of this information. But all of this is on this activity itself is on the education.ti.com website. And as Brad pointed out, down here are the links that you would want to follow if you wanted to get this activity and do it. And obviously there are a variety of different courses that this is tailored to as well for you to be able to use with different levels of students and different ages of students that you might have in your classroom.
So the placement of the field goal post has changed over time. Initially, the field goal post was on the goal line, right? And as you can see in that lower left photo, it maybe benefited the offense at times and hindered the defense, kind of an extra blocker on the field. So the NFL got wise, and I guess there's some safety protocol that they called in, and they moved the goalposts back to where they currently are, which is at the back of the end zone. So if you're not a football fan or an avid, watcher of football, you might see a team lining up on, let's say, the 10-yard line. That's where the kick is going from. So you might assume it's a 10-yard field goal, but they do count the distance from the beginning or the end zone to the back of the end zone in the field goal distance when they're calculating those. So, and then the placement of the ball, they usually snap the ball to someone holding the ball at 7 yards further behind the yard line. Okay, it's an arbitrary 7 yards, but over the course of time, they've kind of calculated that that's enough distance that they need, or the shortest amount of distance that they need to be from the actual yard line of scrimmage for them to kick it.
And Brad, somebody had pointed out that one of the other factors in kicking a field goal might be that you have to get it over the defense who's trying to block it. So I think we'll be able to discuss that a little bit as well. But yeah, without those 7 yards, you're not going to be able to get the angle elevation that you might need to get it over the defense as they're trying to jump up in the air and block your kick. But then at what point do you reach too high of an elevation where now that's impacting the distance that the ball can travel? So all areas that we're going to explore as we go through the science and math behind this moving forward. So here's a little trivia. You can also put this into the chat window on the side. What is the record and who holds the record for the longest NFL field goal?
I think Valerie Gibson might know the answer to this one. $65 has been said. 60 it was made last weekend.
Way to use units in there. That's great.
A lot of mid-60s up there.
Yep. I believe all those at some point were records, but not the current record.
I think one of them was.
I think the first value that came in,
Good.
66 yards. And I don't know if anybody has ever seen how far 66 yards on a football field actually is. Just to be able to kick the ball that far is pretty amazing. And then to do that accurately is even more amazing. So then the next question, who kicked it?
I wanted to.
We might have some Ravens fans.
Yeah, could be. Some Baltimore folks.
He did not play for the Washington football team, no. Who kicked it? Yeah,
There it
Justin
is.
Tucker. Justin Tucker is a pretty impressive guy. He also is an opera singer, along with being an outstanding kicker. So he does currently hold the record for the longest NFL football. he may have, but we're going to move beyond that because there might be some Ravens fans online that could get upset. So, but he does hold the record for the longest field goal ever. And one of the things to consider that would be a factor also is he kicked this in Detroit, which is a dome. So how does those environmental factors also go into play? The previous record, I believe, was set in Denver, so you're in mile high. So then the atmospheric conditions are different for how you're kicking. So all of those are all factors that the more in detail you want to go, the more you can start building these pieces into the puzzle. Again, we're going to stay at a pretty elementary level, perfect conditions, no wind, no rain. No, nothing that would impact the kick besides the kicker themselves. And that's the math and science we're going to delve into here. So one of the things, obviously, that a lot of people have talked about has been the angle. It did barely clear, actually. It hit the crossbar and bounced through. So he hit the crossbar at the right angle, unlike the former Bears kicker who didn't. So one of the neat factors on that you can use with the Nspire is the geometry page. And so one of the areas that you can simply go with is if you can find an image like this, you can put that image into a geometry page or a graphs page, either one. But on the geometry page, then what you can start to do are put things in like segments or rays where then you can measure the angle between them to determine what was the angle that this ball was kicked at. And so now you can start getting to questions of, you can read on the field and see that they're on the 39-yard line. So if he's kicking from the 39 plus the 10-yard field goal, that would be a 49-yard field goal. So if he's kicking at a 27-degree angle from 49 yards, at which velocity does he need to be able to kick it at to make it? Oh, but now you have to factor in that the goalposts are 10 feet up. So how does that impact? So you can get some really, really complex problems that we're going to go through here and show you how you can use different functions to be able to solve those. So we're going to get into the path of the field goal. Brad, do you need the screen again so you can show
Please.
this? All righty.
All right, so I haven't taught various levels of math, algebra, geometry, trig. We barely ever touch upon parametric equations. I think it's kind of, for sometimes it's an afterthought, just not necessarily in our curriculum sometimes. So what this allows us to do, all right, is to introduce some parametric equations. And what's nice about it is it has a hook for the students, or at least a bunch of the students. They've all seen at some point, a football game. I'm sure they've seen a field goal as well. If not, we can introduce them to that. So on the Nspire and also on the 84, you have the ability to graph parametric equations. Right. So, in order to do that, right, in the menu, we can change what kind of graph entry it is. All right. So most of the time we're dealing with functions. All right. But we have a lot of different other options in here. So if we went down to number 4 here, parametric, you notice it has a X and a Y equation. All right, it's with respect to time, and we can talk about how we're stepping the function. How much it changes each time. Right. So having done that, I had already pre-entered this particular parametric equation. So if we take a look at it, I'll go and change it to parametric. There it is. And so here, what we did is, this is the equations for the various components of the flight of the ball. Cosine of 43, that's degrees that we're kicking it, 43-degree angle. 72 is going to be your feet per second, all right, as far as it's going to be traveling. So I know a lot of physics teachers want to be using meters per second, but since we're kicking it for yards, we were sticking with feet per second in this particular instance. All right, so if I go to trace this, all right, we could see very similar to that activity that we had on the 84. All right, we could trace it. And as we're moving along, we could see our X and Y values and the various times that it's taking. And I set my scale here to every 30 feet, which would represent every 10 yards. So 10, 20, 30, 40. Here's 50 yards, all right? And again, here's that height of 10 to see if it would cross that crossbar, all right? It's not elegant. It doesn't have a lot of pizzazz with the actual crossbar there. And as we see it moving here, right, you see it's at 12.1 there. And then as we get to the next one, same thing happened. We're beyond it, right? So we'd have to actually change how we're stepping this and see, see our various changes, right? So that was the design of this, all right? And then moving on from that, because this is a static model, right? This is already 72 feet per second. It's at a 43-degree angle. You want to give the students the ability to experiment and play and ask those questions. Is the angle more important? Is the speed more important? So there we go. So what I did is I created some sliders for this one. All right. So in the program, we put a V and an A in there for the velocity and the angle. And now we can change those different velocities. So here we could see if we have an angle of 21 degrees, by changing the velocity, we could see the range increases. All right. But, not tremendously. All right. So we could also take a look at if we're changing the angle.
Right? So, even with that, you're kicking at 74 feet per second. That's a pretty solid velocity you're kicking at. It's still not going very far, right? So then now you're playing around with the two different variables in there. And while you're watching this and seeing how the angle is changing, just to talk through the equations there to make sure everybody understands where they're coming from. What you're solving for is the X and the Y distance, the position someone had written in there before with respect to time. And the V that you're using would be the result velocity from having the X and Y components. So then the V cosine A would be using your trig with the angle of elevation to solve for what is the velocity in the X direction. And then the V sine A is then finding for the velocity in the Y direction, the vertical direction, based off of that resultant velocity, which is that 61 value. And then that negative 16, being a department chair, I have observed Algebra 2 teachers teaching a lesson similar to this. And when they're using that equation afterwards, I've asked them, well, what does that negative 16 represent? And unfortunately, I've had several of them who don't know what it represents. It's just the equation that's in the textbook. And so understanding that the acceleration due to gravity is negative 32 feet per second squared. Yep, you got it, Ray. And in the equation is the velocity times time plus 1/2 the acceleration times time squared. And so half the acceleration, negative 32, that's where the negative 16 comes from.
And one other thing with this, where I'll go to the next page.
And Josh, you're correct. We're assuming the initial height here is 0 since we're kicking off the ground. So yes, there would be an additional term that you would add on to that Y equation that you would factor in the initial height you're kicking from. Because we're kicking off the ground, then we don't need to include that in the equation, but good point.
And so one of the participants talked about a defense, right? So I'll jump to that one right now, where here we're just going to make an assumption that this is the defender, all right? And so what we did is this is 21 feet from the kick, so that's the 7 yards. We're assuming that this defender is roughly around 6'3", 6'4", and has a reach where they're able to, I guess, flat-footed or even jumping, reach about 9 feet. So you could have your students, to play around with what velocity or what angle. Here you got a 43-degree angle. What's the minimum angle that they have to have based upon their velocity to be able to out kick that or get that above that reach to give them a chance. So again, you could play around with these things where students know what some of their minimums are, maximums, and gives them a idea of what they could do with a range of values, right? So kind of, when we start talking about, domains and ranges, we talk about, what's feasible, what's not feasible, and if they have, they don't have a strong foot, they're only kicking 61, their minimum angle here has got to be greater than 31 in order to just clips that. So again, that's another way of just playing around with these various pieces to see how they're going to make it, and so on. So this is, again, an application of being able to use some of the parametric equations with the students. You don't have to go fancy with the sliders. You can have them experiment. The students will be able to put numbers in back and forth. You also have to, kind of give them some parameters of what's real. Is someone going to be kicking it at 100 feet per second? What does that mean? As an algebra teacher, teaching unit conversion, that's a kind of a nice, segue into, what is that in miles per hour and so on. Is that, even doable? So, a couple of things like that. So.
And you can easily tie in the previous, Brad, if you could go back to that.
Yeah.
You can easily tie in the two screens together now and asking questions from 1.4 where you're looking at that angle. So go ahead, Brad, if you can move back to 1.4.
Sure.
We're living here, so
yep.
Sorry about this if it doesn't work out quite right. So you had 64 as your velocity and 32 as your angle. Mm-hmm. So now you can take a look at, well, all right, so if we are kicking with this velocity and that angle, how far are we going? And you can approximate there you're looking at what, 137-ish feet that you're able to go for that. Mm-hmm. So now what happens, Brad, if you decrease your angle? So take that from 32 and just bring it down a little bit. What happens to the range?
Decreases.
Okay, and if we increase that a little bit, now we're seeing the increasing range. So there comes also a point of no return where it starts to go back, and actually the slider only goes to 44. Once you go beyond 45, then that range starts coming back again. So where is that inflection point that you need in order to be able to make the kicks, and how does the angle you're kicking at impact the range for the velocities? What would happen if you kicked at a really low velocity? And when you start getting into the actual science behind it, where you start getting air resistance played in, where it's not perfectly parametric, you can now start asking questions of, well, why is it that that you're more likely to have a 50-yard field goal blocked than a 20-yard field goal blocked? So let's see if you have some thoughts. Why is it more likely to have a 50-yard blocked than a 20-yard blocked? Any thoughts from the audience?
Yep.
And why does the angle need to be lower? More angle choices. Why does the lower angle make it travel farther? What about the velocity? So we can really start getting into some pretty in-depth questions here, right? And how does the angle impact the horizontal velocity versus the vertical velocity for the same resultant? So a lot of different areas that we can now start bringing this into, of not just the science, but also the understanding of the science, the understanding of the trigonometry of how a larger X component versus a smaller Y component impacts the overall resultant and the direction, how far it can go. As you bring in dx, VXT into the dx, well, the lower your angle, the more the VX is going to be. So your dx is going to be longer. So the ball will travel farther. So there's a whole area that you can go into super far in depth in terms of what are the advantages and disadvantages. So thank you for your participation in the chat. All very good ideas over there.
I'm going to kick it back to you, Todd, for kicking lesson.
Yes. Close.
Close. Coming soon.
All right. Okay, so in the slideshow itself, everything that Brad was just going through in the Nspire is all here. So if you're going back to reference this later, all the equations are included in here, some diagrams to help understand the trig of what's happening. Just so if you're looking to replicate this on your own, you can do that. We'll provide files and information for you. But we wanted to go through and make sure that this information was provided for you. And one of the things that Brad talked about was the need to have the units put in. And some of that also is just the way that the Nspire itself operates, the operating system works in terms of the built-in units that it works through. So one of the important areas here is the ability to convert and be able to move back and forth between systems and understand what one speed correlates to in another speed based off of units. And so typically in a physics classroom, we're going to be talking more about the meters per second, but we also have to deal with the limitations of what we have. And so being able to convert between those two is important. So most of the kicker foot speed as it goes through for NFL kickers is somewhere in this range of meters per second or this range of feet per second. So this is how some of those sliders were built as well, and the parameters were built in the sliders based off trying to make this realistic. And that's something that I think most of us try to do in our classrooms, is make the situations model reality as much as possible. A whole nother area that you can get into here in a physics classroom is looking at momentum and collisions. And you've got the elastic collision of kicking the ball, and how does the velocity of the kicker's foot with the mass of their foot correlate into the velocity the ball actually leaves at versus what the leg speed is going through. So many, again, different areas that you can tie this into and bring this into in your classrooms as you keep moving. Here's some pictures that we found, again, of the blocking of the field goal and different angles that you're kicking at. And I don't know if this is the same kick from the video, Brad, the doink. But what I see here is that the ball is going to hit the linemen of the Bears and not even have to worry about getting up to the defensive guys trying to block it. So just another area of the Bears not being very good. But again, looking at how high do you need to kick the ball? If this is at 10 feet here, this person is jumping all the way up to about 12 feet to be able to block that field goal. And so then what are the ranges of realism that you could put in? How does a high school game and high school size players compare to NFL players? And so if you're trying to work with your kids and their ability, what's the reality for them based off what they're going to go out and face on a Friday night or a Saturday morning? So where my brain went with this as we were going through the creation of this is I want my students to be able to experience this, to be able to have some data, to create some data, to be able to analyze, and then start tying it into these real world situations. So anytime that I can have a lab that is based off of my own students doing something, I think that's the best way to do it. So we'll have students walk and run on their own and get their own data. And one of the things that one of the applications we discovered during COVID time was this Vernier video analysis. And we're going to show you briefly how that, just the ability to use that here and how that then ties into coming back to a simulation. So we're going to get into a little bit of coding here in a minute. And one of the beautiful things of the coding aspect of this is now with data, you can start running simulations, and the simulations you can use through the code that Brad has really created here. I just more challenged him of different ways to make it look fancier, but he really did all the coding behind it to make it run. So all you need, I saw a question come through, all you need for this is a camera. You need the application itself. You can get a 30-day free trial, or there's a per student user fee that you could also get to use this with. And then just anything that you can take video with. We've had students we're a one-to-one with Chromebooks. We've had students use their Chromebook cameras, and sometimes it's fine, but oftentimes the resolution isn't there. So we find better luck with students using their smartphone. The videos tend to be of higher quality to be able to analyze. So once you have the video, you put it into the application, and through the analysis, the point of this is not to teach how to use the Vernier video analysis, but to watch it work. But within here, it basically does a time period by time period, frame by frame implementation. And so I had to go in and set up a scale. So I knew the distance between the two posts here. This is at a local baseball diamond. I'm in the outfield of it. So I had to measure this horizontal distance to put a scale in, set an origin where basically the origin is going to go from where I'm kicking from. And then from there, when you run the program, it will go through and slow down and frame by frame. This is a punt, I understand. But you can go through and mark where the ball is on the screen at each of those moments, and then create position and velocity versus time graphs using the scale that you put in and using the information from the kick. So now you can have kids go out and they can actually record themselves doing a kick and get this data that comes through here. I'll do it again. The punt is better, more impressive than my field goal that I have in a minute. But now as you go through here, you can get the statistics of your kick. So here I'm just modeling, turning off the features that you have. And from the stats, now you can start to get this information on the screen where you have your mean value, you got your minimum value and your maximum value, the red being the X velocity, and then down below in the screen, it doesn't show on this one, but you can also get your Y information. So now you can start talking with students about, well, what does this information represent? Obviously, we're representing velocities. Well, which one do we want? Do we want the minimum? Do we want the maximum? Do we want the mean? It's going to be different if you're looking in the x direction versus the y direction. So again, now you're starting to get into some deeper analysis of the data itself. And in the x direction, if there is no wind resistance, there's nothing once it's kicked that's going to speed the ball up or slow it down. So your x velocity should be fairly constant. So I look at using the mean velocity in the horizontal direction as you're taking whatever is that average going across. These dots are put in by me, not the computer system. So there's going to be a little error in where I exactly place the dot as I go through. In the y direction, then I'm going to use the maximum velocity because that's where I have just kicked the ball and gravity is just starting to have its deceleration on the way up. So those are the values I'm going to pick when I'm moving forward. So now, here we go. Now as we move forward, here's the actual data going through and talking about that information. So now as I take the mean data, another good question here is, why is this negative? It's telling me that I had a negative velocity. Well, why is that? Was I really going that slow? That's right. The way I had to set up the origin in order for y to be positive is I actually had to rotate the whole axis. And so to rotate the axis, that made the left direction negative. So that doesn't mean that the ball is somehow going backwards in time. It just means it's going in the opposite direction of where the positive value would normally be set up. So this is just a directional piece. So now as you're talking about absolute value, here's an example of that, right? It's the value is what we care about. And then in the y direction, choosing, again, the maximum value as it's leaving the foot before the deceleration vertically from gravity on the way up. So now with that information in meters per second, now you can get into the vector analysis to determine what is the resultant vector. And so based off of that, my punt was going at this direction, 54.95 degrees above the horizontal at this meters per second speed. And again, as we get into the simulation I'm about to show you here, based off of what we need to do that conversion. So it converts to this feet per second. Do I need to convert the angle at all if I'm using degrees? Does that change if my the initial speed changes? Wait time. The angle doesn't change, right? And so all we need to worry about is the value of the speed, not the angle that it was kicked at. So very good. So again, trying to get mathematical thinking and reasoning and what am I converting? What am I not converting? Why am I converting this and not that? To get students to think through what this information means. Too often we have students just calculate a problem, get an answer, and not understand the context behind it. So now we're bringing that context in. Yeah, so now here is me attempting to kick a ball off the ground, and then we'll show you the simulation here in just a second. But trying to kick a ball off the ground for this one. So my punting was better than my field goal kicking. I can also say that as a 43-year-old man who does not go out and kick very often, my leg hurt in places I didn't know it could hurt the next day after going out and doing a few takes of these. But here's an example of my field goal kicking. I didn't slip and fall, at least. There goes the ball. And again, we're getting some measurement data now off of this as well. And if you notice, there's a spot, well, there was a spot at the beginning where the data was the X direction. It separated quite a bit from there. But same thing, I went through, plotted the data, got the information from it. And so then I was able to get my field goal kicking data over here in terms of the mean and the maximum as we went that way. So using that information from the field goal, we can now go into the program that was written that we're going to now run the program, or in a minute run the program once Brad talks through the code itself that goes into writing the simulation.
Okay, so when we were asked to do this webinar a long time ago, it was under the guise of that, it's been done with the 84, and we'd like to see if we could kind of recreate some of it with the Nspire and with some Python language. So got thinking about it and trying to figure out how we're going to do this, using Todd's physics ability with the parametric equations, we were able to do this, right? So it's nice that they have this ability to code in Python now. So there's a bunch of at the top there's some importing that's been done, and that's this ability to plot points, and some of these other things where it's got time and math, and then the system import. All right. So the reason why we had to import time is because I decided to put a little delay in some of the graphics that we were going to do. The math was because we were going to be using the sine and the cosine functions. And so this initial part here where it says user inputs, that's going to be getting feedback from the user, and it's going to be you guys in a few minutes. All right, so we want to know how far we're going to be kicking this, what angle we're going to be kicking, and what velocity in feet per second. All right, so those are going to be some things that we're getting from the user. How to convert the distance from yards to feet. So the scale was in feet, and then the way that the sine and cosine work in Python is using radians. Right, so we had to do some conversion to radians. So again, this is a lot of math class stuff that we can use with algebra 2 students. Never too early to introduce it a little bit to algebra 1 kids, just to give them an idea of what's going on. We had to create the window and the scale. All right, so the window was going from 0 to that distance, which wound up being the distance in yards, but I put an extra 10 yards in there, so that's what that plus 30 is. And then the grid is just what you would see when we plot it. There was some graphics that were created, the goalposts. All right, so those were put in there as well. They're just basically some lines that we created to simulate goalposts. So there's some aesthetics in there and some setup. Right, the next page has actually the actual program. So we had to increase time. All right, starting with time equals 0. All right, in this for loop, it's going to plot all the points that we did along the way. So that range from 0 to 60 is just kind of a, it's a guess, or it's plotting 60 points, and a lot of times it'll keep running past it with the ball already hitting the ground. So that A piece there, that was your X value, all right, and your B is your Y value. I chose A and B just because I don't like using X's and Y's sometimes in programs, because it sometimes picks up on different X and Y values that are within the calculator. So I just stayed away from them. And here our sampling is every 0.05 seconds. It's going to plot these points. I put a little sleep command in here because this is the way you could actually see the plots going. All right, if you didn't sleep it, it would just kind of race right through it because the program's working really well. At the end, we figured a way of determining if the kick was good or not. So when we show that one simulation before on the 84, you got it close and you didn't know if it made it or not. It was at one point it was above, but it was not far enough, and the other point it was below, and it was way past the distance. So we did a little calculation here. We had to figure out the time at which it was going to reach that distance, and then we substitute that time value into the Y value to see if it was at that height or not. So that's the guts behind this program. This will be included in the files. You can use it as is. All right, there's no need to change anything with it. If you want to change it, feel free. Just shoot me an email and tell me how you made it better. So I'm always looking to see how we can do that. So we're going to analyze it.
You did this on the CX2, right?
Yes, this was a CX2, and I assume just because I didn't spend any time with the 84 Python just yet, but I assume that this is we could duplicate this for the 84 Python with the plot lab.
All right. So then in the elaborate part, where I said before with the elaboration, that's really where we as the teachers in the model, we and the teachers are going into more information behind it. But I also want, as I mentioned before, the students to be able to elaborate on what the information that they're getting is and what it means, and is it realistic. So I put some of my my data in from before, and I decided I would go with a 66-yard field goal. And then I put in the information that I had from before when I was punting the ball. I had gone through and I had calculated that. So again, the angle and the feet per second in there. And as I kick this one from 66 yards, look at that. Yeah, so Justin Tucker's got nothing on me. I am a better kicker. I am a better opera singer and definitely more handsome than he is. I think we can agree that all three of those things are probably false statements. So, is it true that your kid who just went out as a high schooler, or me as a 43-year-old man, is going out there and being a better kicker than Justin Tucker? Probably not, right? So, is that data that I had used really the right data? Did I use the right data, or did I analyze the data incorrectly? Because it doesn't make sense that I would be able to do that. So moving forward, as I looked at the data from before, I noticed that there is this kind of weird area here at the beginning where some of my data isn't quite working out. Before with my X velocity, now it's staying very consistent as we're going through that way. And from a physics perspective, again, the X velocity should be staying constant because there is no external force acting on the ball in the horizontal direction once it's moving through the air. So I went back to my data and I selected the area, the range of data that would correlate to what was most likely the accurate information, where I was able to get to the video, frame it out right, and go through there. And so now as I go through with that information, I get some drastically different data for my kick. My X velocity is significantly less. My Y velocity is, or I'm sorry, my X velocity is less than it was before. My Y velocity is significantly less. And now as I put those two in, I get a very different speed and I get a much lower angle. So both of those two are different. So if my speed is lower and my angle is lower, how is that going to impact my actual kick? So now this data is probably more realistic. So now, again, that evaluate piece is really designed for us to evaluate our students' understanding and our student learning. But I think there's also an important piece for the students to be able to evaluate, does this actually mean something? So now when I put in probably more realistic information to that kick that you saw me do from 66 yards out again, there's the angle. Here's the velocity conversion in feet per second. Yeah. Nobody's looking to sign me. Ray, you're right. No NFL contract. Now, I do actually have video from a couple years ago, but I didn't include it in here. But I got to go to Hallis Hall where the Bears practice, and I did nail a 30-yard field goal there, and that was right after the double doink. So I did think about going for an open tryout for the Bears, but decided that that probably was not worth my time or energy. So the beauty of this program is now in this setup that we've gone through here over the last few minutes is the ability to now have students collect their own data, their own information, and then be able to put that in and now start playing around with simulation of, okay, well, what could I really make a field goal from? And what does this information say? What would happen if I change the angle versus the velocity? Because I probably can't have my leg go faster than it is right now. That's probably the maximum velocity I can move my leg at. But what happens if I change the angle? Right. And so now you can go through it and modify really quickly on the fly and have students start to figure out from their data what they could do differently. Right. This could be done at a football practice, at a football camp. There's a variety of different ways that you could use this and bring this in. And the beauty of this also is while we're talking about field goals here, you could adapt this into a variety of different opportunities where you could start talking about a home run derby, right? And you're talking about the launch velocity that you need to have, the angle and the velocity it leaves the bat at. And you have to modify a little bit to have that. But again, the same program and opportunity can be brought into multiple different areas. When I was watching the Bears game this weekend, one of the things that happened when a field goal was made is NBC had a logo that came up and said good from, and then the distance it could have been made at. Well, they're doing the same calculation. They're looking at the velocity that the ball is going through the goalpost, the height it's going through the goalpost, and figuring out how far back the kicker could have been with that kick and still made it. So there's a lot of real world applications that are being brought in through all of these. And this simulation helps to make that more of a real feel for the students and start to understand applying the physics and their own ability to that. Brad, you want to talk about
why don't you toss me the control for this a little bit so we can talk about this? That's a little bit. All right.
All right, there you go.
Got it. Cool. All right. So here it is. Share. All right. So I'm going to take you a little bit through the development of this program. So you saw a little bit of the ins and outs. And so this program, as I build them, sometimes I name them. This was I was tinkering with the field goal program. And so we run it. I said, well, this was a 45-yard field goal attempt. We're going to hit it at 38 degrees at 70 feet per second. And so when the kick went up, you could watch the path go, and you're holding your breath, making sure you might make it. And again, you get to that point where it's like, don't know if we made it or not, right? So that's where I decided to put in if it was good or not. So we're going to use that same values. Go to the next page.
And what I like about this version versus the one that we had on the screen before, Brad, is how you actually put the units now in for what are you being asked for to help give a little more direction to the students so they can hopefully make sure they're putting the right, are they putting in feet or yards, meters per second, feet per second, where are they using? So I like that you added that into this program.
And then I decided that we go with the yellow goalpost for the way it's in now and a little bit of grass on the field. And then as we can see here, it wasn't good. Right, chain them up a little bit short. All right, so we had to play around with it. All right, so Todd, you can see the chat. I can't see it right now. So let's have the audience call out the first. How far should we make this one?
Let's see in the chat window. What's a good distance kick from? 43 yards.
Okay, 43. And the angle we're going to kick it at?
Well, 66 came in. I think they meant that for the yards, but let's make that the angle.
66, okay. And how fast are we kicking this? We'll go back to the 66 in a minute.
What do we want for a good feet per second?
I'm going to go 72. So this was the latest challenge that Todd sent to me. He said, how about a blue sky background? And he kind of asked me to do this on Sunday. So I was able to accommodate him. So here it is, kicks up. I don't think this 66 angle is going to be doing too well.
That's really more of a punt.
And
all right, so now, Brad, well, how come the program stopped with the ball midair?
Yeah, so what wound up happening is, if we go back into the program, when I sampled it and said, how many times is it going to run? I ran it 60 times and it plotted 60 points. So at that point, it was no good. So we could increase that number of samples or number of times it runs through it that many times. So let's just run through.
It probably did hit the scoreboard there. So one of the things, again, from a physics perspective that we try to get students to understand is that what impacts the time in air is the height. So because that was such a steep angle, it went at such a high height, the time in air was much longer. And because of that, the 60 times through the program didn't have enough time to complete the kick.
Is that 66 yarder? I don't know if it's got the distance.
Well, if it was me and my fantasy kicking from before, it would have been good.
So, all right. I know Michael needs some time to wrap up, and we got to make sure some people get a chance at the technology drawing.
Thanks so much, fellas. All right. So, as promised, that big drawing tonight, one lucky winner is going to receive a TI graphing calculator choice, and tonight's lucky winner is Andrew Gerard. So, Andrew, congratulations. We'll be in touch over email the next couple of days to get some information from you and hopefully to figure out which graphing calculator you're going to be choosing. So, congratulations, Andrew. And to receive a certificate of attendance, go ahead and click the link that is going to appear in the chat window. And if this link doesn't work for any reason tonight, just hang tight. You'll automatically get a follow-up email in a couple of days, and that follow-up email will contain links to the certificate, the documents, and the recording. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. I know Brad and Todd posted their personal information. That's really great if you have any specific questions about the webinar tonight or any of the content. But if there's anything else that's burning that you have a question about, feel free to give us a call, 1-800-TI-CARES, or drop us an email, ti-cares@ti.com. We'd love to hear from you. Huge thanks to Todd and Brad. Todd, thanks so much for putting your kicking skills on display for all of us to ridicule you for years to come. This is recorded, so we can play this on slow motion and really analyze and break down your kick and all the things that were wrong with it. So, Todd, thanks so much for letting us do that to you, and thanks so much to both of you guys for putting everything together for tonight.
Thank you.
Got it. Thank you. Thanks everybody for being here with us tonight.
That was a lot of fun.
I second that. Thanks for joining us, and we hope to see you back online next week. Have a great night.